Hi, welcome to the Sugar Math Practice Lab, Learning Through Practicing. And we are in this unit, we try to practice the problem related to the exponential growth and the decay type of the problems. And this is our practice set number 1 here. So in this set, we're going to talk about the general exponential growth and the decay type of the problems here. Okay, so that's the video number 1. And so let's go ahead and start take a look at our first problems here. Okay, the first problem is telling us populations. Okay, so let me see. Okay, so all right, so our populations of the Pozola developed with a constant relative growth rate at 0.7944 per member per day. One day is 0. On the day 0, the population consists of the 2 members. Okay, find the population size after the 6 days. Okay, so this is a very typical exponential growth because it's the relative growth to the population itself, right? So it's 0.7944 per member per the per member per days here. So if we write it, we know we call it, this is 1 over p. Then this is dp dt, right? So this is the relative growth. So this will be 0.7944. Then when we discussed the exponential growth and decay, we said if you kind of take integration both sides, and I know we did not talk about the integration yet, but that's why we said, okay, now, we just need to remember this formula. So I want to find my population. So this is what we have, right? So we say it's the PT is equal to what? The P0 E what? EKTs here, right? So the in here the K is your what? Your relative rate, right? Okay, so now we be able to input our values here. They did give us, this is what we call this the initial value. So let's say that on the day 0, that's what is P0. I have 2 members here, right? So that's why I know this value. What is this number here? This is 2, right? And then the EKT, so the K is tell us is what is the relative rate is 0.7944. And also because it says this is a relative growth, right? So I put a positive, I don't put a negative in front. And then last things here, they say, hey, find the population size after 6 days. So my T is what? My T will be, what is the value, my T? My T will be 6, right? So now you put all this together. So we said is 1 equal to the E, 0.7944 times 6. And then you can get the answer is about 234.99. So you have about what 235 members was developed here. So first problem is a very easy one. It's very, very straightforward type of the problems, right? Okay, now let's take a look at the second one. See here, the second problem, they tell you a bacterial culture initially has 100 cells and grows at a potential rate proportion to its size. After an hour, the population has increased to the 420. Okay, so now the first, let's try to write all this information. So the formula we have is what is the PT is equal to the P0 EKTs, right? Okay, so the problem is that, okay, so part A, they say find the expressions of the number of bacteria after T hours. So that's what we have is a PT is equal to the P0 EKT here. And then it tells us, hey, my culture initially is 100, right? So that means this 100 is my initial value. So it's 100 EKT here, okay? And now, okay, so the part B is here. So let's say find the number of the bacteria after 3 hours. So I will need to use the information here. So in here, let's say after. So for here, it said after 1 hour, the population has increased to the 420. So I need to go to figure out what is the relative rate, right? So I have 420, and this is 100 E K. So how many hours? 1 hours, right? So that means I put ones in here. Now I can try to solve this. So I can say the EK is equal to what? 420 over 100, so it's 4.2. So that means the K is equal to what? Natural log of 4.2 here. Okay, so now we want to find what is the number after the 3 hours here, right? So in here it said after the 3 hours. So what I need to do, so I would say population 3 is equal to the population 0. So 0 is 100, and E, and what is E? Is natural log of 4.2, and that after this is 3 hours, right? And if you want, you can simplify a little bit. So this one's here, you can put the 3, the inside, right? So you can put the 3 inside. So this is a natural log of 4.2 to the 3's powers, right? And then you see here the good, the natural log and the E cancel. So that's why you will have 100 times 4.2 to the what? To the 3's here, correct? Okay, so so the answers here will be close to, is about 7408 and the 0.8. So it's about 7409 here. Okay, so part C here. Okay, so part C, I want to find the rate of the growth after 3 hours, right? So remember, this is very important here, because remember we said dP dt is equal to P and K's, right? That was the initial formula. We said, hey, the rate of the change equal to proportion to the population. That's what this is. We call this exponential growth or decay type of the problems here. All right, so now they want to find is after the 3 hours. So I'm looking for the dP dt after the 3 hours, right? So that means I'm looking for the dP dt, and this is really is P prime, right? That's a derivative after 3 hours, so it's P prime 3. So P prime 3 is equal to the P times K, so it's P the 3. And now we already figure out what is the K is a natural log of 4.2, right? Then P3, did we already figure out the P3? Yes, the P3 we find in the part B here, right? So it's 100, and so it's 4.2 to the 3rd powers, right? So it's from, so here is what we figure out from the P3 in the part 2 here. All right, and now you will have, this is put into the calculator, you will get this is 10632, and this is a bacteria per hour. That is how fast the rate of the bacteria grows after 3 hours. Okay, so the last part of this problem is when the population will reach the 10,000. Okay, so now you just put your PTs, right? So it's 10,000 is a PT. You initially start is 100, right? E the KT. So what the K here is a natural log of 4.2 to the T's power. Am I right? Okay, so now you can solve it. So you can divide it by 100, divided by 100. So this will be 100 is equal to E the natural log what be the natural log of 4.2 t's, right? These two you can cancel that out. So it's 100 is equal to what? 4.2 t. How do you solve this? Take a natural log of both sides. Correct? All right. So you take the natural log of both sides. Then you will have a natural log of 100 is equal to t, the natural log of 4.2. So what is your t here? Will just be the natural log of 4.2, natural log of 100, and you put it into your calculator, it will approximately give you 3.2 years. Okay, so this problem here, so it's very interesting problem, and I think here we are kind of very familiar with the other part, and the rate of the change. This part we need to be very careful here. All right. Okay, let's take a look at our other problems here. Problems here, they will tell you there's a bacterial culture grows at a constant relative growth rate. The bacterial count was 400 after 2 hours, and the 6 hours is 25,600. So I want to find the relative growth rate here. Okay, so let's try to put it down here. We still, remember we use the PT is equal to the P0 EKTs, right? Okay, so now let's put it here. So the first thing here is 200 after 2 hours. So I have a 400 is equal to what? The initial rate, I don't know, right? So it's P0E. What is the relative rate? I don't know, but I know it's 2 hours. And then the next thing here, they said after 6 hours, I have 25,000 is equal to the P0 E the K 6 years. Right? So that's how do we set these equations and set this equation. So now we have two equations with two variables, and then I need to solve for what is my P0 and what is my, the relative growth rate. So what can I do? Let's divide these two here. So that will put 25,000 divided by 4,000, right? So 25,000, this will be P0 E the K what? 6, right? So this is a 6, and then this is a P0 E the K2. Then P0 cancel. So 2,500 divided by 25,600, right? So I'm sorry, here is 25,600 divided by 400 here. So I will get that this is 64 is equal to the E. How many K here? 4 Ks here. All right. So now you take the natural log of both sides and solve for K. So K is about 1.0397. Okay, so what is the relative growth rate? So the relative growth rate is about, let's say we'll put it into the percentile. So it's about 104%, right? So this is 104%, 104% of the growth, the relative growth rate. Okay, so now they say the second part, they say, hey, what is after you find the growth rate? What is the initial size? Okay, so I I just put it, so 400, this is 2 hours, right? So it's the P0 is equal to the E, so it's 2 hours, and what is my K? It's 1.04, right? Okay, so this is 1.04, then I can find that my P0 is equal to, this is E, the 2.08 and the 400. Am I right? Okay, so now let's now so in here we can find it. This is the P0. So what is my P0s here? So the P0 is about what? It's about the 50s here. Okay, and now instead of the last ones here, it tells us it will find the express rate of the bacteria after the T hours here. So I will say the PT. Okay, so I can say the PT is equal to the P0 EKT, and the P0 is 50 times the E, K is 1.04 times what? Times T here. Okay, here some people, instead of you divide it into like the decimals here, some people would like to put this in this way here. Okay, so the way they put, like they like to do this, they take the natural log both sides here. So the 4K is equal to the natural log 64 here. Okay, so then the K, so K will just be 4 natural log 64 divided by 4, right? And then the people will say, okay, this is a 4. The natural log 64 is 2 to the what? 2 to the 6 powers, correct? Now you can move the 6 to the front. So this is 6, 4, and the natural log 2. Or you can say the 3/2 natural log 2. Some people like to put it in this way. That's fine. It doesn't matter. So like in here, you can, if you want to put it this way here, you will say this is 50, and the E, the K is 3/2 natural log 2 and times T here. All right. Right, so now in here, so you will say here, and the people, so some people like to simplify this a little bit. So this is 50E, then you can move this as a whole thing inside. So this is a 3/2 and the T here, right? Then here, these two is the inverse function, and you can cancel out. So the final answer, it will be, what is the final answer? So this will be 50s, right? And this is the 2, so 3/2 is 1.5, so it's 1.5 T. So you can simplify to this, or you can put it in here. So it doesn't matter. That this form, like this form is just a little bit, it's kind of like a nicer looking form here. Okay, so now the next one's here. So let's see here. The next problem here is continues from the. So it said to find the number of cells after 4.5 hours. All right, so that means I'm looking for P, the 4.5, right? So it's 50. I know that the formula is 2 and 1.5 T's, right? So you see now why you like that nice formula here, right? So this is 50 and this is 2. This is 1.5 times 4.5, and you will get about 5,382. If you like, okay, so of course you can do this. You said P44.5 will be 50, and the E, then you say 1.04 times 4.5, right? So it's the same way. You can get you can get a very similar answers here. Okay, so now the part E is the rate of growth again. So remember the dP dt is equal to the K T's, right? So now they want to find the rate of the growth at 4.5 hours. So that means this is P prime and the 4.5. All right, so the P prime 4.5 will be the K. What is the K here? So K is 3/2 natural log 2. All right, and then the P, so here, remember here, right? So remember here, this is the P's, right? That means it's the population at the 4.5 hours. So now in here, you can have a piece here. So this will be 50, and then this is the 2, the 1.5 times 4.5. Cool. And then this one's here, if you put it into your calculator, it will be 5596. So that means that after 4.5 hours, the growth rate will be about 5,596 bacteria per hour. All right, so the last part, this one is very similar like the one we did before, is when will the population reach the 50,000? So you will say 50,000 is equal to what is the initial? Initial is 50, and then you have a 2, and this is 1.5 T, or you can put like this way, 50,000 is equal to the 50 E, the K is 1.04 times T. Either way, right, you will get the same answer. So like in here, so if I cancel the 50, so I will get a 1,000 is equal to the 1.5 T. Now you log it both sides, right? So you log it. So this is natural log 1,000. It will be equal to 1.5 T natural log 2. All right. So now the T will just be equal to the 1.5 natural log 2, the natural log 1,000. And you will get approximately to the 664 hours. That means about 6.6 hours, and the population will reach to 50,000 here. Okay, so this is our video number 1. We did 3 problems, and all those 3 problems are very, very basic and classical, you know, the exponential growth and the exponential decay. So remember, right, it's all based on the formula PT is equal to the P0 EKTs here. All right, and so the problem can give you the different parameters and what to find the others, right? So sometimes it will give you the initial value, sometimes it will give you the time, sometimes it will give you the relative rates, right? All right, that's it. And now our next video, we're going to take a look at some very, very special case. Those are the, we call it a half-life and the double life case here. Okay, so nice talk to you, and looking forward to talk to you in our next videos here. Okay, bye.